So there's Viz for scientific data and Viz for data science. Viz for data science is a course I think is awesome. Viz for scientific data is also cool, but it's not data science geared.
The second one, the scientific data.
Scientific data is coming from like a simulation of 2 or 3 dimensional data.
Yeah, they have to read this one.
Yeah. So let's get started. So the web page for the entire school computing is down, so you can't see the schedule. So you can't see the course notes I prepared for the lecture today, which we'll do on Wednesday next week anyways. We've determined it's not school computing problem, or that's what they think currently. So, but if you're questioning where's the web page, that's why you can't see it. If you need anything, you can email me. I'll send you a direct link over the weekend. I think. Oh, it's back up. I just checked now and I couldn't bring it up. Oh, okay. Great. Yeah. So there's assignment due next week. So by popular vote, by people who got here early, I'm going to switch the topics today. I don't know what this will mean to the schedule, but I'm sure it'll be fine. So I just gave a guest lecture in a economics class on the theory of science or the philosophy of science about how does machine learning fit into this. And so I don't know, maybe I'll give this again today. I think it'll probably be fun, maybe, hopefully. So please stop and so we'll do this, stop and ask questions. And so I'm going to kind of, it's not really data mining as much as supervised learning approach to the world, but I think it's relevant, and you probably don't see this elsewhere in the curriculum, so I figure it's okay. So let's see, the context is these are markdown slides and they don't always fit on the page, but okay, I will try and say what's missing here. But so the context is I was speaking in the economics department, which specializes in kind of these science where they're trying to do causal inference and Bayesian modeling of the world. And they're doing things like, it's not rendering very well, but they're trying to do a mechanistic view of science, right? Which is what science has been probably very successfully, I'll add, for the last 100+ years ago or so. And basically how science would work is that you wanted to understand some physical or mechanistic process of the world, and you would make some observation. The example is supposed to be force equals mass times acceleration, F equals ma, right? So it's one of the laws from Newton. You could somehow measure the mass of things and the acceleration of them and kind of quantify the force. And through a bunch of experiments, you might realize that this law tends to hold with things, right? You can make the right observations. And this was a guiding principle for a lot of science and engineering the next 100 years after this came. Now, like a slight caveat, right? You probably, if you took a 1000 level freshman level course in physics here, you probably learned equations like this, and they are not exactly true. There's the also notion of like relativity, and then beyond relativity, there's like a quantum understanding of things, and there's more and more detailed things. But for 100 years or more, this law, force equals mass times acceleration, and other laws of physics, and still what you probably learn in a freshman level course, this is basically true, right? There's some simple, elegant hypothesis that can possibly be correct. So it's simple and it can still be correct. And so all components to this can be accurately so measured. And the field of experimental physics is often, how do you make those measurements, even if it's not so easy to actually do? Okay, and the classic workflow, which you can't entirely see on the slides for whatever reason, is that you would start by making a simple hypothesis about the world, typically simple that you should be able to verify. You would then go and collect the data relevant for that. The hypothesis might be from some observations first, but then you go collect the data to try and evaluate it. And then you apply some statistics afterwards to try and evaluate whether your hypothesis was correct. All right, so this was probably this is how I learned when I was in high school. This is what was science. Right, this sounds reasonable. Yeah, no? Yes, okay. All right, so science B, I'd argue is what is different, and that the goal is to try and predict the future, right? So so predicting the future is hard, but we're not trying to understand the mechanism that leads to that future. We're not trying to understand the laws of the universe in that way. We're just trying to predict what the future will be, and the key high-level assumption, we'll get deeper into these, is that the future will look like the past itself. Okay, so we can learn from what we've observed to predict what will happen in the future. We're not trying to learn like a mechanism, at least not initially. So the components we observe may be very noisy. They might be incomplete. There might be some mechanistic aspects, some things that are actually driving it that we're not actually observing in the process, right? There could be stuff inside the body that's actually driving how we react to some medicine, but we can't physically actually measure all those things. We can only measure some observations and want to predict what the outcome will be. And we can collect a large amount of data. So we're in the era of like big data, right? So we're good at sensing. In the old kind of laws of physics, you had to collect this by hand, write it down in a notebook. There was a whole notebook science that I learned when I was in high school. Now it's all through computers. We record this sort of stuff, right? So so the workflow of how this would work typically, right? And so this talk will be mostly about this type B, kind of thinking about this type B of science, this lecture. And so you would first collect lots of data. And so this changed around the year 2000. That's when Google started becoming a popular search engine. And one of their goals was to organize the world's information. The Sloan Digital Sky Survey came out online. This was when in astronomy, instead of an astronomer would get time on a telescope and look at one star and take pictures of it for a few days and then sit and analyze it for like a year and then publish a paper, Sloan Digital Sky Survey went and took pictures of whole swaths of the sky and put all the data online, basically. And this completely changed how people did astronomy. This is how almost all astronomy works now. Sometimes they direct for specific observations, but we build the first kind of complete human genome. Instead of studying individual genes without context, we tried to build the whole genome, right? This all happened around 2000, right? And so then this is the first step: collect lots of data. A lot of your projects were basically like this. You started go find a data set, right? That was like the first the second task. So then the second step is to define what a good prediction looks like. And this is important. You have to say, well, what would it mean for a good prediction to be? And I'll specify this more. And then you search for any function that does good on this prediction rubric. Okay. And I don't want to this is basically what machine learning, and I'd argue that a lot of modern science has moved to this type B over the last 20 years. This is basically the dominant form of how we do science It's not all of it, but it's been moving largely in this direction. Okay. Let me talk about what are the rules of the game of machine learning. Hopefully some of this will be familiar to you from what we've talked about in this class or earlier classes. But the first and a really important one, which may or may not be true, but we assume that we have a data set X and it's IID from some distribution mu, right? You know what IID means. All the observations are the same. They're all identical. They're all from the same distribution. This mu represents the world that we're drawing observations from, right? Every data point is from this space. You can think of like you could press a button and another data point would come out. And the goal is to understand mu, something about the world, to predict something about mu, right? This kind of fits in the context of what your projects are doing, right? And this can be repeated many times. I can get n observations where n is like a lot. Okay, for you, this hopefully will make sense. The next one is we're in this supervised world, which is mostly not what this course is about, right? This course is mostly the unsupervised world, but we're in the supervised world. So every kind of data point xi is paired with an outcome, right? We observe the stock price for j days in a row, and then we predict the outcome is what it is on the next day. We can make a bunch of observations like this on the same stock, on different stocks. We can do this for the weather or something else like that. Okay, and so we have this paired outcome observation, and this allows us to say the goal is to try and learn a function to predict what this outcome is going to be, right? So, so I'm not going to worry about what the space of functions are. In fact, we've moved less and less worrying about what the space are. But in a machine learning class, you'll learn about different types of functions that you could try and learn how to learn these functions. And then we're going to use so the thing is we don't need a lot of statistics and modeling here. We can use cross-validation to evaluate how well we're doing, right? So we take the data set X, we actually randomly split it into two sets, the train set and the evaluation set. These are disjoint from each other. And so we can do whatever we want on the training set, including looking at the labels. And then we want to evaluate what's off the screen here on how well we do on the evaluation set. And that will tell us how well we hope it will generalize to new data. The idea is that because the split was random, then the evaluation set represents a random subset of the observations. And so how well the prediction of the future does there gives us a guess of how well we'll do on future data that is also coming from the same distribution. Okay, so this is a great equalizer. A lot of the rest of the world needed to do a lot more modeling of what was going on here. You had to think a lot more about the statistics here. We don't really need that. We can just measure how well we did on the evaluation set. Kind of, yeah. Yes, great question. So if you don't know the underlying mechanism, how can you say the data is IID, right? Yeah, so you don't really know it's IID is one thing. This is a conceit of this whole view of the world. The other view of the world has other challenges as well, right? How do you know you have the right data, and you still, how do you know it's representative anyways? But does it depend on knowing the mechanism to know whether the data is IID? Well, the idea is that you're collecting it from the population you're hoping to study, and you're making observations from the population, and you can observe the outcomes after maybe a treatment, or you're trying to understand if if I make these observations, who will live longer or who will not live longer, right? Which one is going to is going to survive or is not going to survive. Right? I don't need to know the mechanism to do this. If I have observations from the population I care about, then I want to be able to just make a prediction on what will happen. Does that answer your question? Yeah. I think this IID assumption is really that. It's an assumption of the world. Okay, but it may not be true in general. So this cross-validation is fairly new idea. I've seen people trace it back to maybe there's actually a very early computer vision task in the 1960s where someone had a bunch of some digits described by holes in punch cards, and they made copies of these, and people asked to replicate some algorithm they had, which is an early version of like perceptron or something. And someone asked to replicate the study, and this guy would make copies of the punch cards and mail them out to people who wanted to replicate the study. And there was a specific training set and evaluation set that was set up in this way. But it really didn't become popular till the 80s. Okay, till we really had a lot of data. It was easy to collect and share data. And even then, like this really didn't take off until, like I said, about 20, 25 years ago, as kind of this whole version of science, when the internet really facilitated the spreading and the collection and storage of data and everything that went with it. So it's really something natural in the era of big data to just, I have so much data, I'm going to save some to use for evaluation. Okay, and it's kind of the great equalizer. I can compare any function I want, different form, a linear regression, a kind of a neural network. It doesn't matter. Whichever one performs, generalizes better, that one's the winner, right? I don't have to worry about doing different things. One of the reasons that clustering, I think, as an area is such a complete mess is that there's no way to kind of evaluate through cross-validation which clustering algorithm is better. You need to do modeling in order to do this. And so with cross-validation, you kind of as an equalizer here. This is kind of a reason why machine learning has really taken off as an important, its role in the world in various ways. Yeah, and it makes sense if your data is truly IID from this distribution, right? Because it means that both your training set and your evaluation set are random samples from this distribution and can be used to kind of learn the principles going on here. But again, we don't need any complex statistics. It just works, right? Okay. Okay, so this is for people who are not taking classes in the School of Computing. I wanted to mention that the computability of these things matter. This is not some existential thing. We kind of, in this world, we want to be able to compute the function f of x, right? So it should be kind of efficiently computable, hopefully. Doesn't need to be efficiently computable. They care, but sometimes the first approach are not very efficient, and then people come up with efficient versions later. But it needs to be computable. You have to be able to kind of write code and actually get the output. The computability can involve, if it includes like some lookup tables in some place, like the inverse of a normal distribution is not computable. There's not a closed form way to solve for this, but there's lookup tables built into these programming languages. All right, so so what's even better but not required is if you can parameterize your function by some parameters alpha, a vector alpha, and you can compute the gradient of the error of this prediction. This allows you to do gradient descent, but doing kind of like these automatic differentiation actually works. This is kind of a big surprise to me that it works so well, but it works. So if you can't compute the gradient, a lot of the methods we commonly use work anyways. So, but you need to be able to compute f. Okay, that's part of the game. Okay, all right. So these are the rules of the game. They all kind of, hopefully, they all seem to you very natural. The IID assumption, I agree. We should question that. Okay. All right, let's do an example. I was actually planning to talk a little bit about linear regression today, so we're not completely off topic. But linear regression, well, you've seen before, you get d-dimensional real data, you have a real outcome, and you want to find a dot product with parameters A, you dot them with xi, and this gives you, this is your function. This is your prediction of y. And I want to, if I'm doing linear regression, I want to find the parameters A. Okay. And in fact, if the goal close is the squared error, and I want to minimize the sum of the squared errors, there's a closed form solution, which are in the class notes on the webpage, which you maybe can't see right now, but there's you can solve this or gradient descent, right? One, linear regression should be something that's not unfamiliar with you. Linear regression, I want to make a point to the kind of economists I was giving this talk to, is not interpretable. This is science B, not science A, and without many more assumptions. And in the next lecture, we will go more into depth in this. But this is especially problematic when the dimension is large. There are collinearity issues where multiple coordinates can kind of encode the same property. Like if you look at the length of your pants and your height, those are really strongly kind of they're correlated with each other, right? So if you measure a lot of things you could measure are going to be correlated with each other, and so when you give a coefficient to a prediction something, it doesn't matter which one you draw from. They both are telling you the same thing. There are confounders things in there that aren't related to it, but might in the data you have kind of look related, but they're not explaining what is going on. Why was the causal thing happening here? And there could be other complex interaction with these parameters. So you can do, so linear regression actually works like super well for prediction. It should probably be, if you have real valued inputs and outputs, it probably should be the first thing you try. And it should be your baseline to predict. And if you beat it, that's great. But if it works well already, then that's even better. But it's harder to understand why it's doing well. I can't understand the mechanism from just looking at linear regression. The actual thing causing the mechanistic property, let's think of why does so why does Advil work, right? You can ask people before and afterwards whether they feel pain. You can give them Advil and their pain will probably go down in a lot of cases. They've taken Advil. Do we understand why Advil works? I think we don't actually understand why it works, but there's clearly a signal there, right? This is kind of what's happening here. We may not be measuring the actual trait of the person inside the body that's actually causing it to happen. We may not know how to measure that, but we can infer that's actually having an effect, right? So I think a lot of science is like this, and linear regression is not, just because it's linear does not magically give you kind of this science, this type A, and interpretability of the mechanism here. Okay. So I was asked to talk in this economics class about this particular paper. There's a paper it's put online about 3 or 4 years ago, which you'll see at the end of this is kind of actually is now maybe it was a long time ago. It got published in like a Harvard Review of Statistics just last year though. David Donoho is a very well-known someone who sits in the space of statistics and computer science and electron engineering for signal processing. And so we'll maybe even talk about next lecture. We may talk about one of the algorithms he's known for a bit. Okay, and so he wrote this kind of this like paper on a point of view, has to address like called data science at the singularity. And it's like, what is the history of kind of, if we think of data science, how is it converging and moving as fast as it's moving? How have we seen so many new scientific discoveries recently, and what role does you know was facilitating this fast increase in scientific discoveries? And I view this as how has science, type B science, become so effective and like influential? And so he coined in this paper something I like a lot called frictionless reproducibility. Okay, this is, and so I'll talk about this. And this is kind of some additional rules on top of this machine learning game that allow you to science to move even faster. Okay, and if you're kind of participating in this, I would encourage you to kind of think about these three properties of frictionless reproducibility to kind of facilitate the role of science and understand how the publication ecosystem works. And so the key challenges here, once we've set up this thing, what you want to do is find this best possible F, this function which is predicting the future, right? And doing this is hard. When I was a graduate student, kind of working adjacent to kind of this area, I've heard this term called graduate student descent, or maybe possibly graduate student ascent, because they're not going into despair. But there would be these common challenges people would work on in trying to come up with a good predictive function. And all the different labs around the world had assigned a grad student, okay, solve this computer vision problem. And they would try different things and come up with the new function F. And then if theirs was better than the previous kind of published paper, then they would write a new paper on this until the next paper came along. And they're just trying different things. And maybe this is 1,000 kind of these AI-powered monkeys at the keyboards trying to do this. And some of the grad students who are taking part of this then were kind of not pleased at this kind of way of thinking about it and comparing them to how their role in the science. They're like, I'm doing real intellectual things here. But the view was not positive necessarily about this, but this was kind of how it worked when I was in grad school. But now I've learned to kind of embrace this. Maybe it's because I'm not the graduate student myself anymore, but like, I really think this is how the science is working, in that we've learned to kind of use the whole community to solve things jointly together. And not every idea will work, but how do we kind of facilitate this towards these big, important challenges in science? And so I like to think of this, if you've been like bowling and you have so how many people have been bowling before? You know what? Okay, everyone knows what bowling is. You're trying to put these pins down and you put these bumpers in the gutters. Then if the ball can't go off the track, right, it will stay in, and you'll probably make some progress. You're going the right direction. It's guardrails for science. Sometimes your ball, if you're really bad, it'll bounce into the other lane and you'll knock someone else's pins down. And in science, this is actually great. But the bumpers, maybe keep them in a bit more, but and that's pretty rare anyway. So you really want to be focusing on specific tasks. And this is, how do we really facilitate this towards really important challenges? And so, okay, so there are these three rules. The first rule is to make your data accessible, share your data, right? Why is this? If you have a result, you say, look, I have a better way of doing something. Well, you better share your data so others can confirm it on the data you have. If you draw a different sample of the same observation of the data, it may actually look different because it's a sample. If you share your data, they will believe the results you actually ran more. And that's one reason to kind of be able to kind of reproduce your experiment. Okay, but more important to this is that you want them to be able to try their own stuff, right, on your data. You want to say, here's how I did, and here's the data. Now you try and do something better. Can you do something better than me on this data? I think I did it the right way. Well, and someone comes along and does it better. Well, that actually advances the science here. And so kind of it's easier access. And again, if you're doing this and you don't share your data, your paper and technique is less likely to be used. They'd rather pick another problem or another paper that used a different sort of data set that was accessible, right? So Hugging Face is kind of a great place to share data and is a real, like a well-known repository for this now. There's also like these UCI data sets that's a bit or older for this. And so there in machine learning conferences, there are these tracks where people just submit a new data set and they try and convince this is an important new data set for the problem. And sometimes that's itself an important contribution. Okay, so you want to share your data so people can reproduce it. The other is the ability to re-execute your function, right? And this can mean different things. You want to be able to not just share your data, but also share the function, which is computable, right? So someone can reproduce what I've actually done, not just they don't have to re-implement it, but they can take your implementation and rerun it, confirm it then. Maybe swap in their their data set, or maybe they want to use this as part of a larger pipeline. It's chaining together a bunch of these functions in this step, and so they can use it as part of it without having to re-implement anything, right? And it could be just executable code, which is better than just describing how you did it in the paper. But it could be more. It could be the weights and the parameters of a neural network. So like the best models from like OpenAI, we do not have the weights and parameters. We don't even know the architecture. But for other ones, like the one from a year or two ago from Facebook, so Llama, we do have the open weights and we know the architecture as well. They may not have intended to release it all, but eventually it's part of it got out there and then they just embraced it. But there are newer models they haven't released. But it's actually really important that we do have the model from Llama for like a year or two ago. It's one of, at the time it was quite competitive and it really gives insight into how these work. There's also other open ones. So the one from Alibaba in China called Qwen is also open. And so we have a number of these models which are available in this way. Okay, and what's even better though is the full source code. Okay, and why this is important is that you can look in the source code and you can actually check, for instance, that someone didn't actually encode the evaluation set inside the code, right? And sometimes this is done not on purpose, it's done accidentally. And so, but sometimes it's done, but you can check if someone is releasing the code. For these large language models, they've released the model, but not the training data set. So we don't know what training data set it's memorized some of the things in the literature, like some parts of books. Some of these large language models have been sued because they can reproduce wholesale chapters of books if you prompt it just in the right way. And those books are under, so have copyright on them. We don't know for sure, but we can pretty much know that some of these models have what they've trained on just by looking at F. But the source code, that's by evaluating the function on certain questions. But this is just the code. So the code and the data, you need to have both of these to really understand what went into here and fully reproduce and kind of analyze this. All right. Okay, so this is the second key thing. Share your function and, in fact, the code. And so, in fact, what a common workflow in research machine learning, or if you work as a machine learning engineer inside the company, maybe without the part where you have the paper. But basically, you find a paper you think is cool, it did something neat that you'd like to work on. You download the code and the function, and you evaluate f on the function f on the data, and you check that it matches y, right? You check the claims. Sometimes you have to install stuff just right and use the right libraries to check the claims, and sometimes it doesn't actually work, but you want to get it downloaded and run. That's the first step. Then you often make a modification to the code. So it's if you have the code, sometimes it's a small but important modification to what they're doing. It might be one line of code, and this can improve this function sometimes by making it closer to the outcomes y you're trying to, right? And if you might try a bunch of them and not all of them do this, but you find one that does do better on the evaluation set, then great, you have improved the function f. You should then write a new paper, release your code, and have the same data set available. And you write a new paper, and there's a cycle basically every 4 months. There are three main machine learning conferences, and their deadlines are spaced 4 months apart. There's a review cycle that is like you get a month to review a handful of papers you're assigned to review, and you get a decision back 3.5 months after you've submitted it. And then if it doesn't get accepted, you have half a month to kind of refresh it for the next deadline. So we've gotten this down to like a 4-month cycle. Yeah. So there's ICML, International Conference on Machine Learning. Deadlines about in end of January. There's NeurIPS, Neural Information Processing Systems. The name doesn't mean that much. It's deadlines the end of May. And then there's ICLR, which deadline was it like a month ago, whenever that was. I forget, but they're 4 months apart. There's some other ones that kind of fit in this cycle as well. There's also computer vision conferences and NLP conferences, but this is kind of the main machine learning cycle in here. Okay, and so this is actually how it often works. Sometimes there are bigger insights and bigger things, but there are tens of thousands of papers published every year in this process. Okay, and rapid parallel progress on a whole bunch of problems. Okay, it's not the only thing that happens in these places, right? But this is a non-trivial part of what this process is. Okay, so there's one piece missing still, and that's to define whatever the challenge is. What does it mean for your function to match the output of the function to match the actual observed outcome? And there's some sort of scoring function. And so in the case of linear regression, that was the sum of the squared differences. Okay, there are other functions that are kind of commonly used here. Sometimes they're simple, sometimes they have other terms in them. And we can talk about those later. And so in order to define this challenge, you need to define what is the scoring function. It could be something simplistic, it could be something more complicated, but some way of scoring how good the actual evaluation is. And you kind of want to hide the evaluation set from the world. Now, in practice, when you release a data set with the paper, you will release this too, and people kind of promise not to train on this. And there's some cross-contamination. They'll only publish a paper if it does well on this set, which has been held out. I used to be much more worried about the leakage here. I'm less worried about this now. It tends to be that there are ways to cheat this, but it doesn't happen very often. That's basically the point. And if it does, people will kind of catch it if you release the code also. Okay, so people have figured out ways to cheat this if you release this, but it turns out not to be too big of a problem in practice. Okay, there's the theory and then there's the practice. In practice, in theory, it's a problem, and practice, it's not a big deal. All right. And so when you release the scoring function, you don't just want to say, okay, it's the sum of the squared errors. If it's something more complicated than that, actually, you should actually write and release the code that allows you to compute this function S, especially the function S on the evaluation data. Grease the wheels as much as possible, right? So someone can recall your code and it recreates all of your plots. It recreates even better, recreates a single number that says how good this is, right? So if you want to say, here's the single number that says how good this algorithm is. That way, if someone does better than that number than you did, they know they did better according to the rules you set. Said these were your rules, and I still did better than you at your rules. So this is kind of the third rule of this frictionless reducibility. So kind of so probably I think I mentioned Kaggle in the project thing and probably before. But this Kaggle website is a popular thing for this, where they set up some competitions, right? So who's heard of Kaggle? Some of you've heard of before. Okay, yeah. So they released a data set and a scoring function, not rendering well for some reason, but not the evaluation data. Often, this is typically how it would run, and they will offer to compute for you the scoring function and the evaluation data. So they'll release the training data, but not the evaluation data. And say they'll do something like every team can submit once a day. You have to register as a team, and once a day, we will compute this for you and give you a score. And they'll keep track of like of a leaderboard of which team or person has the highest score so far. Right. And then they'll announce some deadline. Say at the end of the month or 3 months from now, we will kind of announce like which team is the winner. For instance, the Netflix Grand Challenge, which I'll talk about in depth later in the semester, was a great example of this. And there was like $1 million prize if they're able to do kind of a 10% improvement on a certain scoring function. And this was super important for the field. And we'll discuss why in a few weeks. Okay, the twist here, which is conveniently off the slide for whatever reason. Again, I can post the full notes, but this is the markdown slides that I gave my notes to an AI last night to make slides for me. This is what happened. It rendered better on a different size screen. But so the twist is at the end of the month, they will not evaluate on XE, which you can't see, but on a different evaluation set they've held hidden and not evaluate anything else on. In principle, this was also from the same IID distribution, but because they didn't test on before, there's no way to have a leakage from this XE. Right, and that's why they may only evaluate this once per day to prevent, what the leakage going on here. Okay, and this was a very popular kind of model for a while. Okay, another kind of game changer in the world of image processing, where there were data sets and challenges for kind of a long time, but they were fairly small and structured. And a big improvement here was this very large data set called ImageNet. And they basically collect a huge set of images and text labels from the captions of the images. And the goal was trying to predict something about the labels. And this was just released publicly. Anyone could work with it. Seemed like a really hard challenge. It was a huge data set, especially at the time. But what happened here was that the evaluation set it didn't care what function was used. And there are all sorts of techniques from computer vision. The history of this was, the history of computer vision was very structured sort of analysis. And then but people have been doing deep learning for a while, but it was hard to demonstrate. No one believed these deep learning people, right? That this was a good thing to do. There's no the theory said it couldn't possibly work, but all these deep learning approaches were completely better than all the other approaches in this. And this is really the moment when deep learning kind of these deep neural networks took off, and people realized these actually work better than everything else if you have enough data here. Yeah. There was a theory of like learning theory, which I'm not going into here, that said that how many data sets you would need to generalize well depended on the complexity of the model, the complexity of the function f. Okay, so people tried to study simpler functions that were less complex because they should generalize better to new data. Because if you were, so there were two issues with it. This was one issue. And because if you had a more complex function, they thought it would overfit onto the data, that it would fit the trained data perfectly, but why would you think it would generalize to new data? It would kind of interpolate the data. That seemed wrong. Now we interpolate all of our trained data. Okay, so this was a big, that's one reason people didn't believe it. The other reason was that training deep networks was not a convex optimization problem. You could define a gradient with them. This is what doing backpropagation does. So you can define gradients on these deep networks, but it was not convex, which means that if you have a function, it's going to converge to a global minimum if you walk in the direction of the negative gradient. It'll converge to something, right? It'll converge probably to a local minimum, but why would it converge to the best answer? Okay, so this was the other reason people didn't believe deep learning would work. It was too complex functions, so why should it generalize? And we can only guarantee converges to a local min, not a global minimum. Turned out it basically converges to a global minimum on the training data if the function is powerful enough. It fits it perfectly. The error is 0, so that's a global minimum. And generalization doesn't work like we used to think it works. There's this for instance, this double descent phenomenon in machine learning. That as you get closer to interpolating the data, it starts to perform worse, and then it works better again. We kind of have some understanding of this now, but not entirely. Yeah. Okay. Is it black? I would argue even doing linear regression is black box, like I was saying earlier. So I still think it's black box. Can you write down with pencil and paper? I mean, these things have the things that did well on ImageNet are now considered small. They only had tens of millions of parameters. So writing it down on pencil and paper take a long time. You can write down with a computer what it is. You can write down what the structure of the network is and how many parameters it has. You can store all those parameters in the memory of your computer. So linear regression, I can write down the function fairly simply. For a decision tree, I can keep the decision tree short, not very deep, and then I can write it down, and it's like this set of rules I follow. Can I get a probability out of this? Maybe. That's for linear regression and like decision trees. If I can get a probability out of those, I can kind of get a probability out of these deep nets, I would say. With linear regression, if you model stuff just right, you say it should fit a linear pattern and there's normal noise to it. And you can say, okay, this is the right model to do here. There is a connection to statistics. Decision tree is harder, although it looks like a logical rule. If you have polynomial regression, it gets a lot harder. If I have confounders in linear regression, it gets a lot harder. Can I get some probabilistic statement out of this? Yeah, people have ways to get probabilistic statements out of it. Do I believe them more than I do with linear regression or decision trees? Or less than I do? I don't know. I believe them about the same. Do I trust the probability? No. I bet the probabilistic estimates, my guess of the probability something is correct when it gives you a probability, my guess is on average is off by about 20%, which is pretty bad. That's out of 100, right? Maybe 10%. Sometimes if it's really accurate, it will know with high confidence. Okay, but if it's not totally sure and it gives you some probabilistic statement, the probability outputs, these estimates are often quite far off. But I don't think that's too different from decision trees or if I have linear regression. And certainly polynomial regression or kernel methods or something else. Yeah, these are good questions. I mean, they can do something like this, but do you really trust it? I don't really trust it. Is it kind of useful as a guide? Yeah, it's useful as a guide, the same way other things are, but it's not really a probability you should trust. The weather prediction, I trust much more. And how much do you trust the weather prediction? So off by about 10% of the chance of rain, maybe. Yeah, it seems reasonable. Yeah, in Utah, they're quite good, much better than they were like 10, 20 years ago. In fact, the weather's predictions are quite good nowadays. Okay, so this really transformed. Here, let's large language models. We talked about I didn't have labels with language, but I realized I could mask out a word and then try and predict what that word was from the context. And this was actually, so I didn't explicitly have labels like I did before, but this was enough to train these things. We talked about this earlier in the semester, right? So these kind of became some tasks, and very quickly, kind of about 10 years ago, this really started progressing once this observation was made. Basically, this observation is really what unlocked large language models. That this labeling as opposed to kind of a structural decomposition of language. Okay, what are we doing? Okay, so the next three of their four frontiers, actually. Okay, can we merge type A science and type B science? There are some efforts at this intersection. One of them I like is called scientific machine learning, often trying to understand physical processes and with some physics underlying, and what they try to predict something, but with some mechanistic property encoded. Sometimes this is kind of as a loss function. Sometimes they control the function space, what the functions can do. So they must adhere to some physical properties. There are some parameters and structure of it they don't know, but some structure of the physics they do know. And they restrict the function class to follow some physics they do know, and they let the rest of it, they let it fix. And how to set this up and predict well with the physical laws. So this is a new area. It's ongoing. There's been some cool stuff here. I followed this a bit more closely 2 or 3 years ago, and at that point, on some really simplistic versions of the problems, some really cool things were shown. And on the full versions of the problems, people don't really know what to do, right? So really big, complex, high-dimensional problems wasn't quite working. And but the very simple, really structured problem, the toy problems, they could get stuff to work. And there's progress in that direction, but it hasn't had its kind of moment yet where we've figured out, I think, entirely how to do this. Or maybe we won't ever be able to reach kind of this kind of the stated goal here. Okay. Another approach is we learn a super complicated function f, and then we say, okay, I've learned to make really good predictions. I have all this data, and I can predict the data really well on the data I've held out and promised not to look at, right? Now, can I go and fit a mechanism to f? right? So I want to approximate f with some simple function, perhaps, right? Or something that I can understand what it's actually doing. This seems like super, super hard. I thought this seemed like a really good way to approach this problem, and I've thought about it. I have one going research project where I got some funding to work on some aspect of this. It seems very, very hard to do, right? So, if you think of like a deep neural network, a large language model, it's got a bunch of these layers. Maybe one of the layers encodes a bunch of information. Maybe we can look at that information and kind of understand what's going on at that one layer. And maybe I'll talk a little bit more about, I think I have a lecture plan that hopefully this didn't replace, that we'll talk more about that later in the semester, or at least some simpler version of that. Okay, but this seems very, very hard to do from my point of view. Seems like a reasonable goal, and I think maybe we'll eventually get there. That we'll be able to use this F to help us interpret the actual mechanism. Maybe at least if it can predict well, then I can simulate a whole bunch of new pairs, many, many more observations, and that will help understand what the mechanism is. But I haven't seen really good examples, meaningful examples of this yet, at least not that I'm aware of. Okay, the third one, I think it's an important one. What happens when the distribution shifts, right? You assume the data was IID, but that's not true, right? This could be that you have a time series you've modeled and you're observing some data, and you can maybe predict what the next day is going to be, but I actually want to predict what the next 10 or 20 things are. And the data is kind of changing underneath me. Or when the prediction you actually make is affecting the world in some way, right? So a lot of how AI differs from what I would call data science is that AI is kind of thinking about not just predicting IID world, what is the underlying science, but is also trying to figure out how to interact with that world. And the interaction means you're changing the world when you're interacting with it. So if you're a robot moving around and you move, something on the table, well, then my observation of what's on the table has changed, right? And you can imagine much more complicated things like this. A chatbot interacting is a good example of how we can do well on this. It's predicting what next to do, and your interaction with the chatbot is changing what the next output's going to be. It doesn't keep repeating the same thing over and over again. It reacts to what you've done. So this is harder, but we have other mechanisms for this. This is, I think, less about science and more about kind of this AI world, and reinforcement learning and the advanced AI course. The AI course and advanced AI course will go a lot more into this sort of things. It's another simpler version where just the distribution kind of shifts once, right? There was a large data we had observed that was one way, and then there was a change, and now we want to predict something on the change, or maybe we have less data. So maybe we can use we don't have to throw away all the old data. We can use it as kind of a week prior. And one really successful example of this is when you have a large language model and you want to tune it for a specific task. Well, what you do is a fine tuning where you train just a few steps of gradient descent for some specific task. And this keeps the structure of language for the most part, but tunes it to that task. And this actually works surprisingly well, how well this works. So this sort of thing works well, but we don't really understand why it works as well as it does. The understanding here is, I think, not fully here. All right, so this I think is kind of maybe a bigger question is, can AI help us do science itself? Now that we've kind of written down this process, can we train an AI to take part in this process or to guide this process? If we set up, frictionless reproducibility 1, 2, and 3, AI can actually participate now fairly well in this. It just needs to train the F. And then we're actually pretty good at training AIs in a very structured sort of format. Here's the data, here's how you evaluate it. find a way that does well on this prediction. Okay, this is one place it does well. But to do science, we actually need to set up these different parts, collect the right data, right? Write the code, and then actually define what the challenge is. And collecting the data, AI can help with this. This is something it can do with a small amount of guidance from humans, maybe automatically. If given kind of stated what the overall goal is, maybe it can do pretty well here. Code, it does very well, right? Producing the code so it's reproducible, this part it does very well. And coming up with the challenges is much harder, right? What is the right way to define the right way of measuring the error? Or just what is the hypothesis we'd like to solve? What about the future we'd like to predict that is meaningful? On the other point, like I don't want to dismiss it. AI has actually hit some like pretty, I think, somewhat disturbing milestones. There was a kind of a real natural language processing kind of AI conference that had a paper that was accepted through the peer review process, basically written entirely by artificial intelligence. The AI, there was a group that wrote some code to automatically write papers. The AI came up with the topic by itself by looking at other papers and code bases and say, hey, what if I changed it to this way? Came up with the new formulation of the problem, and came up with a new algorithm. It published the code and the data on automatically on the websites. It created a GitHub repo just for that paper. It ran a bunch of experiments, and it completely wrote the paper in the right format. Okay. Now, this research team, they did this a bunch of times, and then some of the times it was garbage, and they said, okay, let's ignore those. And a few of them, they said, these look kind of good, and they submitted them to conferences. And the first several times they did this, no papers were accepted. Okay, which is good. But last year, there was one paper that was accepted. Once it got past peer reviewed, they retracted it. They said, we're not actually going to publish its proceedings, but here's the paper anyways. People are really mad, right? I peer review something like 50 to 100 papers a year. It takes a lot of my time. Rather not be reviewing slop from AI. I think my time is fairly valuable. And people are like, is this real science? I looked at the paper. It wasn't so horrible, but it was completely uninteresting to me. It was like some signal processing kind of approach. Yeah, question. Well, this one was not slop, but a lot of it is, right? If the goal is to get as many papers as possible, you really stress test this. So there were probably 50 AI-generated papers that had a reasonable chance of getting into a good conference that were submitted. This is my guess, that were submitted before this one got in, right? Probably the other ones that not get in. Still, the acceptance rate's like 33% at these conferences, so most don't get in. But when the acceptance rate of your process is 2%, okay, then you're not helping, right? It's contributing to the load. And if everyone was doing this, it's going to overwhelm the system mostly with garbage.
So given this, what do you think the future of coding is?
Of coding? I mean, coding is a completely different thing, right? Because AI is very good at writing code. The department's offering a class called vibe coding next semester, which sounds like awesome, right? I mean, it's the people running it, they have been playing with these AI things for code for a while, and they kind of have a good sense of what will and won't work. But you'll kind of learn the best practices of using AI to help you write code, and it can automatically generate a lot of code. And sometimes it's really good. Sometimes it can rewrite and fix bugs in your code. And sometimes it introduces really subtle errors that takes you as long to, figure out what went wrong as it is as if you had written it yourself. I think it's not, when I first 6 months ago, I'm like, okay, this is is clearly happening. That's the thing. Not as convinced now it's ready for prime time. Some companies like NVIDIA, apparently everyone is mandated to use cursor, right, to integrate into their coding. Like this happened, like 9 months ago. NVIDIA is a big, important company, right? So like it's changing things. How much is it helping? It's certainly helping in some things, and it may slow down other people who are really efficient at these things already. What is the right way to do this, right? What prompts do you have to give the AI to know that you're going to get the right code? Are those prompts just another programming language? People are asking this question. Okay, just there's also, think of this view from compilers, and I'm old enough that I had a course where I had to write something in assembly. It was not the whole course. Like friends of mine who went to other universities, their first course at the university in computer science was an assembly course. Okay, I'm post punch cards. Okay, I'm not that old. All right, but I've had to write some code in assembly, and when I've written code in like Fortran, pretty low level. I grew up basically writing C, right? C is kind of low level, not as much now. People mostly using Python, much higher level code. It automatically does a bunch of stuff for you. The libraries in Python are amazing. The biggest change for me has not been C to Python, the language, but has been how powerful and easy to use the libraries are. You don't have to write a lot of this stuff anymore. I wrote my own data structure library in C because the standard ones I didn't trust that much anymore. Now they're super good. I probably can't do as well as the libraries. I could back when I was a student. I could write better, I think, than a lot of the libraries. So the programming has changed in that way, and it will continue to change. What is the abstraction that we interface with to that? There are downsides to this, right? Some downsides, like C, gave us just enough power to make some pretty horrible bugs in code, right? That were very hard to debug because they were too complicated. And this is maybe where we've learned our lessons and the next will be better, but I don't know. I think we're going to make some horrible, horrible bugs this way. Yeah, so that's the future of coding. So back to AI for science. There are companies, several companies with good amounts of funding from VCs, where their short-term goals are to write papers that are getting accepted into the venues that are peer reviewed. This process of AI writing papers. And their vision is that the AI will automatically move science forward and help us understand and discover new science. And the way to quantify that and encapsulate that is writing these papers, right? It will make these discoveries automatically. And there's some people who totally believe this is the way forward. This whole process can more or less be automated. I have my doubts. Yeah.
When you write a bunch of papers.
Yep.
But the point is that you want to do it by AI fasting, so you need a way to evaluate faster, but that's not happening.
Well, there's the other side of it is that a lot of the conferences, so there's a problem with some of the people tasked with doing peer reviews. I'm asked to do a ton of these every year. We go and ask AI to help us write the peer review. You can give the paper to a language model and ask it to write a review for it. There are lots of reviews publicly out there, so there's lots of training data. And this is also a problem because the AI reviews are not as good as human reviews. But a lot of places are starting to do where they will pass it to an AI to do a review and make this part of the process, but explicitly labeled, this is what AI thought of the paper. There are issues with this. This has been used by judges in the legal system. Should someone get parole? Okay. And so, and there was a very famous piece of software called Compass, which took a bunch of cases of people going up for parole and trained on decisions made of did these people get parole or not, And it was provided by a company to judges to help them make decisions on this. And well, so the short answer is it picked up on a bunch of intrinsic biases. It did not look at the gender or ethnicity or certain demographic information, but it picked up on this based on the zip code where the people live. Those things are very correlated with the zip code and these other traits. And it picked up on these other things, and its predictions were very skewed in certain ways. And in fact, you could kind of swap the kind of non-important information like their home address and certain parts about them and have put in data that had basically the same crime, the same time served, everything else the same. And it would tend to pick up on these things, and the traits that were correlated with people who were non-white tended to not, those people tended not to get parole. Okay, so this is the context of the software. This was an AI software. And so what do judges do? Well, they weren't said, okay, just use this blindly, but you can use it and also make your own decision. Judges tended to say, well, the AI said this, I'm not sure I'm gonna trust the AI. So even though they should have said, well, this is a case that I don't know, I shouldn't trust the AI, I should make my own decision, that's probably when they tended to trust the AI. They still relied on it in the cases that which were not as clear. So that's kind of the worry of what would happen with this reviewing of the papers. You give the AI review and the AI says, no way, or it says, oh yeah, this just reminds me of this paper from 2 years ago, it should be accepted. Well, that paper, that happened 2 years ago, which is a long time in this kind of singularity process. So maybe it's picking up on old trends, stuff that's already been done. So I have my doubts on how this is going to help. And this is really the bottleneck here. Yeah, so this is a big challenge. The person power of people reviewing these papers is really, really stretched. And that maybe is the bottleneck. Yeah, I mean, internally, these companies that are doing this, they are throwing it into these AI reviewers to help them determine, did this work or not, without them internally reviewing it. And only the ones that pass the AI reviewers do they probably actually have a human actually read and verify. So like, I don't do this. Most people don't do this. I'm sure some people probably do. We've been given a lot of feedback if we're going to grade your assignments with AI, that we should be very clear when we are doing this. The guidance we've been giving on when you should do this is if, hey, you're going to write code, then I'm not going to personally have the chance to read all of the code that you wrote, but I can have an AI give you feedback on it. So it's either 0, I can give no feedback and I will review something at a later stage, or I can give you free intermediate feedback from AI. That seems to be like a good intermediate step. And maybe that's also good for papers. You can submit it to an AI and get a first impression. Should I even bother submitting it to the conference or not? And maybe we don't get as many junk papers submitted because AI helps people self-select. Maybe this is helpful. But I don't know if it'll solve it completely. Yeah, okay. So this was what I had planned in this guest lecture, which for this economics class, I just redid. Here, if you're in the supervised learning space, essentially, you can do this. You should aim to your science goal to set up this frictionless reproducibility where you're sharing your data, sharing your code, and explicitly describing the challenges and even the code to evaluate that. There are lots of challenges in doing this and how you select the data, how you set the challenges that AI is not very good at doing, but where humans I think need to be part of this. Again, in data mining on the unsupervised setting, we have not talked about a lot of these things because we don't have the supervision of the labels to set this system up. And so I've been trying to say, how could we get into this with like the self-supervised stuff we talked about? I'll talk a little bit about regression and what does it mean to do feature selection or distance metric learning. We touched on this, but like clustering, I don't know how to fit in here because there's not a well-defined challenge, for instance. So it still may be useful, but and dimensionality reduction still may be useful, but it takes more, it's less automated how to do that. And so it's harder to fit into this paradigm. But I think nonetheless is an important part of doing data science process. All right, we'll stop here and we'll get back on the regular schedule on Wednesday.